Good evening, one and all. We welcome you to the first talk of the Leadership Lecture Series this semester. The title of the talk today is Aerospace Systems Engineering, The Way Forward. It is my great pleasure to introduce to you our speaker for today, Professor Amrutur Anilkumar. Amrutur Anilkumar is a professor of the practice of aerospace and mechanical engineering at Vanderbilt University. He has been a NASA investigator and operations manager of microgravity fluid phenomena experiments conducted on space shuttle flights and on the International Space Station. He is the founding director of the Vanderbilt Aerospace Design Laboratory and faculty advisor to the Vanderbilt Students Launch Team, which has won 4 back-to-back NASA University Student Launch National titles. Dr. Anilkumar was recently honored as the 2016 Faculty Advisor of the Year and the Abe Zarem Educator of the Year by the American Institute of Aeronautics and Astronautics. He has also received many other awards from NASA, AIAA, and Vanderbilt University, including the School of Engineering Award for Excellence in Teaching. Dr. Anilkumar graduated with a BTech degree in Mechanical Engineering from IITMadras and an MS and PhD in Mechanical Engineering and Aeronautics from the Graduate Aerospace Laboratories at the California Institute of Technology. Now, please join me in welcoming our guest for today.
So, right off the bat, I'm honored, but more than honored, delighted to be here. I think it's a great opportunity. The timing may not have been the best, but sometimes it is hard to mix business and the pleasure of coming here. But I'm very happy that there's been an opportunity to visit and give this seminar. And for the interested audience, I'm sure even if we run over time, we can keep ourselves quite occupied in the process. So what we are talking about is a change in the way we look at engineering. Are we going to be continuously looking at engineering as a combination of traditional coursework and then like an assembly line, getting a job and allowing the job to dictate what we should be doing? Or is there a responsibility for the schools to produce a product that is more on the finished side that can potentially be a path breaker into the future? If given the choice, you would probably pick the latter because the part one is congested. Why? I think one of my friends here gave a talk about edX, Coursera. You can enlist online and do coursework. There is the other aspect that any school potentially can use the same textbooks and teach the same material. Then the question always arises, so what's the big deal about an IIT? So what is the big deal about an IIT? Maybe one of the big deals about IIT is some smaller deals like this, where we come and listen to these kind of talks and enrich our horizon. Maybe the connectivity that these kind of talks provide and the exposures that these kind of talks provide, when you put a face to it and realize that there is a possibility, it will motivate you to do more things. All right? So maybe we should look at it that way. Then there are other things I'm sure IIT itself will tell you, that it's about our laboratories, it's about our training facilities, and we're not congested. We have all this landscape and all that kind of stuff. Okay. So but for you, the big question should really be, what do I do to shape myself going into the future? So along those lines, let's look at this seminar. So what I'm talking about is a new paradigm. You might even say this is an old paradigm, but we will see. Maybe by the end of the 60th slide, it's just my warning that there are 60 slides, probably we will be believers in this process. Okay, so what does aerospace systems engineering do? It designs, studies, simulates, and implements the interconnections and the interactivity of many systems and subsystems necessary for a space-based asset to survive its intended environment and perform its functions. So you say, oh, no big deal there. You can always design something to perform its functions, but then you add this caveat: flawlessly, every time, year after year with no possibility of maintenance or repair. Oh, this would be wonderful. If, for example, anything that we design has been put through this kind of an understanding and this kind of an analysis, then we will probably be better people, we will be probably happier people, we will probably have a confidence to do other things, considering that this does its job. If you train a dog and the dog does the same thing, then you say, well, don't worry about it, he'll do the same thing. But suddenly it gets up and barks at you or bites you, then you say, what happened? So I think you want to make reliable engineering systems, and aerospace engineering provides the pathway to it, because failure is not an option. So I think the concept of failure not being an option should really be ingrained into everything that we do, everything that we design, everything that we participate in. I think we will be a better society, maybe a better people, a better civilization, and whatnot there. So if only we could implement this in infrastructure design and maintenance, healthcare delivery leading to better survival odds, traffic and safety, resource allocation and distribution, disaster preparation and management. Well, we wouldn't be going from disaster to disaster. We wouldn't be talking about what if scenarios, what if we had known this before. You can't go about digging sand out of a riverbed and then wonder what happened to the river, it all went underneath or something. You got to be thinking. You can't build a huge water tank next to a railway track and say, I didn't realize this water tank will break, and then blow the railway track away, and then the train coming by gets all blown out of shape, and then some 200 people die. So I think as a civil engineer, you don't just build a water tank, you figure out where you put the water tank, and you figure out that the water tank will not fail no matter what the circumstances is. But given that it might fail, what scenarios have you thought through as to what else can be compounded by that scenario? Okay? Otherwise, you will have these kind of unmitigated disasters, and you move from disaster to disaster to disaster, and you invoke the higher being at levels where he or she should not be invoked. Man should really be doing things to a point beyond which he or she should take over, and you don't bring him down to a level field where you haven't put in your efforts. And that's what systems engineering says from a cultural perspective. And maybe, so it's not about building your spacecraft, and you guys are already building a satellite. It's about where do I take this concept and intrigue myself into possibilities and solutions. That's what you should be doing. All right? So I gave a preamble to what I meant. So you do a risk hazard analysis, and then you do a failure mitigation. So as I said, it could be a water tank. You could have a trivial consequence. It could be maybe a rain. It could be a minor consequence, maybe a gust of wind. It could be a moderate consequence where maybe the plumbing system might break up. It could be a high consequence where there could be an earthquake. It could be a critical consequence where you did not design it, where you designed it with all factors in mind, but there were factors that were unknown. For example, the steel or something else that you put in was not of the caliber. It had internal failure lines through rusting or whatever, and the whole thing could be an unmitigated disaster. If it's very rare, you do a color coding, and if it's very likely, you run through the color coding. Green lighted, yellow, think through, come up with mitigatory approaches. Red, don't go there. Red, don't go there. So don't put a water tank near a railway track. It's a red thing. Well, don't give me that BS about there is just so many people, there is no other place, so you have to put it on somebody's head. That's not going to work. All right? What does our popular culture say? Well, our popular culture, on the other hand, tries to stay away from rational approaches and science altogether. It likes the hero approach, Take this thin guy, put him on boxing gloves, and he can knock the punches out of this guy. You know that's all BS, that's not going to happen. But it makes you to think like that and kind of feel good about it. But solid, substantial, concrete engineering should not be working this way. Should not be leaving those odds out to these kind of scenarios at all. It would make a society very cynical. Nobody gets onto an airplane thinking about the odds of failure. The can for failure has been kicked so far away, like 1 in trillion, that even a 100-plus-year-old lady can just sit in there and get off on the other side of the earth without batting an eyelid. The same lady probably can't even handle the barking of a dog or something, right? That is the engineering that we as in IITians should be thinking about. We cannot all be ducking for cover with some silly arguments, all right? All right? There are not too many systems engineering terms to talk about in India. Dr. Kalam is one who comes to mind, and ISRO comes to mind. We have to give credit where it's due. As a nation, I think we have learned how to build satellites and build launch vehicles, put these on proper trajectories, manage them, maintain them for tens of years. But as a nation, I don't think we have learned how to build a car, a reliable car, or any of those kind of things. I don't think it's 100% engineered from scratch or anything like that. But you can say that about the ISRO. So that kind of systems engineering principles, that kind of design has not gone in. And that shows in everything we do. We don't have those kind of reliable systems at all. Well, all that is fine. So where am I heading here? So the big questions for a university is, well, I just sat down upstairs and I had 6 of our classmates within plus minus 1 year talking about the great things about IIT Madras and all that. But even for you folks who are all here, back here now, how do we stay relevant in this disruptive world? Well, we can block off and make that entry to IIT Madras difficult and then say we are an island of success and glory and all that kind of stuff. But at the end of the day, people will always ask the question, so what is going on? Okay? And what is disruptive world? I'll come in the next presentation. But we need to always think about how are we going to get noticed? How are we going to get noticed? Are we going to get noticed? Well, we have all these publications, Google Scholar citations and all that. Man, that takes insane amount of time. That is a pyramidal structure that takes a long amount of time. I think the real strength of a university, if everybody looked carefully, is the strengths, and those strengths have to be harnessed in the right way to build the engine that can potentially bring the name. How do we combine, this is the question I asked, so I put that in gold, academics and competition to keep students interested. It's very competitive to get into IIT, man. There's all those test papers that you do, this, that, and all that kind of stuff. I can tell you from our own experiences and things like that, it's very competitive, and you miss one thing, and then after you hand in the test paper, you'll be sitting and biting your thing about, God damn it, I wish I had known this thing. You know, so with that kind of capability to handle pressure and competition, are we doing a good job with the same kids? Are we putting them through a creative, competitive environment? Or are we just saying, okay, this is this is a quiz, this is a thing, you do this, you get that, you get that. You know, it's like you get your degree and you get out kind of thing. So that's an issue that's always bothered me, because I've always been a very competitive guy. My resume runs really long on that part of the game, and so I wanted to do that. To me, there's a subcontext to this. Space has been a subcontext for me silently through my undergraduate days at IIT Madras, but more openly right after I finished my BTech. I switched to aerospace engineering and things like that. So space has been a big issue for me. All right, so what do we mean by a disruptive world? Circa 1700 to circa where we are, newspapers are dead, magazines are dead, radio is dead, television is dead, cable news is dead, web browser is dead, Google might die, smartphones are there, iPhone is there, things like that. So basically, pretty much, nobody's going to go to read a newspaper. It just put there, the dog will be barking, and put it in the trash and move on. Nobody has the time, nobody wants to do it. Things have changed, the world has changed. So it's very, very, very disruptive. In our era, to get a phone line, you had to be a VVVIP. I could go to Caltech, but my parents did not have a phone line. They had to dig that nonsense and all that stuff. Suddenly, not here, not in this system, somewhere else on the earth, cell phones came along, and even the lowest of the low has a cell phone, which is thereby the cell phone, in my opinion, is the greatest invention man has ever made. It is the first thing that's been given to everybody. Now, everything else is a mess of things. You don't get, everybody doesn't get it. So, well, this is the kind of disruptions we have to be careful about. Everything that we know and we teach, man, we teach such a great electronics course and all that. Tomorrow, the whole thing will be turned off base. Electronics itself as a field is completely gone. Digital electronics sounded very interesting, but I don't know, when I went to grad school, it's just not there. It's just not there. It's just not there. Okay? So we have to be very careful about this. So is space the new frontier? So let's have some fun with some video, okay? Is that a video okay?
What are the important steps in the evolution of life? Obviously, there was the advent of single-celled life. There was differentiation to plants and animals. There was life going from the oceans to land. There was mammals, consciousness, and I would argue also on that scale should fit life becoming multiplanetary. I think if one could make a reasonable argument that something is important enough to fit on the scale of evolution, then it's important and maybe worth a little bit of our resources.
That's Elon Musk. A little bit about Elon Musk. Elon Musk is not going to go down in history as the guy who came up with PayPal. He wouldn't want anybody to know about it. He would rather hide behind it because it's a simple program and an algorithm that basically cuts some cash out for every transaction. He wants to be known for something substantial. So you want to be very careful. These disruptive leaders are not dumb. They didn't hit upon something. All they did was they were the first to come up with this idea that you can make money out of an infrastructure that's already set up. So if you go about doing something else on that infrastructure, you better be smart about how to turn that into something more creative later on. Elon Musk is talking about disrupting space launch. So Bill Gates, the owner of Microsoft, is not some guy who decided I'm going to put this Microsoft software into every computer and therefore make money. I mean, he is a disruptive, creatively disruptive guy who even decided that a Harvard undergraduate degree had no value for him. He wants to bring balance in the world to the best way possible, though at the end of the day, resource allocation and redistribution is not possible. But in everything else, from disease to everything else, he wants to be right up there. So today's world is being disrupted continuously, and we need to take notice. And many of you who want to be these great entrepreneurs better do a reality check about the substance of what you're trying to do. Don't just jump into the bandwagon of trying to make quick cash. I don't think it'll do our institution any good, frankly. Be careful about that. All right. The past drivers of innovation have always been from the government and academia. It's kind of like where ISRO is today. There's a kind of a collusion between government and academia. The government holds the hands and stuff like that. They're the more classical guys. Put them in black and white. Werner von Braun, you might have heard of, but if not, go and Google that. Carl Sagan, who basically was behind the Voyager missions and things like that. This is what you are interested in, color. Give me some flavor. And today's trendsetters are Jeff Bezos from Amazon.com and then Elon Musk from SpaceX. Jeff Bezos wants to be not probably known for Amazon.com either. He wants to be known for Blue Origin that wants to send people to space. Elon Musk, as I said, wants to be known for SpaceX, all right? So there may be opportunities in the future where the India space program may be looking for entrepreneurs who probably want to take on some of these space business and kind of keep it clean from a private enterprise standpoint. Maybe there may be opportunities there that one can creatively look into. All right, then you have Bert Rutan, the quintessential designer of airplanes, who came up with this suborbital spaceship one that Richard Branson is now trying to fund, but Branson is not any of those, these kind of inventors, so I'm not going to put him on this pedestal. All right? Disruptions all the time. You think of your satellite, David is helping the process. OneWeb wants to launch 900 of these satellites, 150 kilograms in low Earth orbit, pretty much providing broadband and internet access from space. That's going to destroy a whole bunch of other systems. That's going to make it simple. That's going to make it different. All sorts of things we need to watch out for. On the launch side, which I'm interested in, by the way, I'm a propulsion engineer, so I ought to be interested in that side of the game. Launch providers traditionally have been government-based, the Ariane European Space Agency, the Proton from the Russian Space Agency, whereas the Antares rocket from the Orbital ATK, which is a private agency in the US, and then there are all these others. NASA so much is not in the launch business anymore. There's Delta, but the Falcon X rockets from SpaceX basically is on the rise. So here is Elon Musk, who starts with an idea. He has a physics background, he can think rationally, he wants to do something important, and he challenges the engineers of today to bring in the new technologies, to bring in the new thoughts. For what purpose? To bring down the cost of the launch. To bring down the cost of the launch. Damn it, some 30 years ago, to make a phone call to US, it would cost some $15, and you get 3 minutes, out of which you 1.5 minutes you're trying to catch your breath. And then the other 1.5 minutes, it just goes on you. But today, it's almost free to make your phone calls, all right? This is the kind of disruptions that is very creative. And on this business, there's a lot going on. So why and what is the question? So let's watch it again. Radical, very radical. Launch vehicle, come back to the launch pad. No cost associated with the launch vehicle. If you can recover it 100%, all you're expending is the fuel. Very nice vertical integration, very simple. All liquid propelled engines, all liquid propelled Merlin engines, 9 times 3, 27. Excess fuel, reverse thrusting, bring it back to the launch pad. Rockets like the ISRO's PSLV, which is a workhorse, is done very well, very complicated. Solid propellant motor, liquid propulsion, cryogen propulsion, 3 stages. Very hard to integrate, very hard to recover the stages. Costs cannot be brought down. So the thing that we need to address, which is really not the focus, but it's a good way to start, SpaceX is talking about offering launch at $5,000 per kilogram into orbit. The Falcon Heavy is talking about $2,000 per kilogram into orbit. Can ISRO ever compete at these rates? Just about when ISRO got ready to launch 25, 30, 35 rocket satellites and stuff like that, here come these guys who are going to offer a price that is very hard to function with. So what's the ISRO's pickle? Construction costs for a PSLV are $15 million. It can do 3250 kilogram into low Earth orbit. And then if you put down the cost of the contractors, insurance, and more, it comes to $20,000 per kilogram. SpaceX is talking about $5,000 per kilogram. It's not there yet, but it is going to get at the neck. It's going to get at the neck. The satellite launch market is very competitive. The price point set by SpaceX invariably makes them the cheapest service among all at present. They have made an effective launch vehicle. They have a cost-effective design, vertical integration, high launch volume. That gives them the advantage. India has made use of low-cost manufacturing along with good success record in launches, but that alone is not enough to maintain a place in this market. A.N. Nair, ISRO scientist and member of the advisory board for the Antrix Corporation, which is really the shopping arm or the management arm of ISRO. So, where is the niche? Is the niche only for a small window of time when SpaceX will take over and eat the lunch? These are the kind of issues that should be worrying the better engineering students. Not status quo, not this, not that. Did you take a supply? Did you take a this? Did you take that? You know, what I'm saying is, how is it? I know you're all interested in competing, making India that great country. We're all, of course, I'm still an India citizen, and compete with China. Everybody wants to ask, are we as good as China? All that kind of stuff. You know, we have IITs, we are better than China. No, we have IITs that are better than the Chinese institutions, but as a nation, we are not better than China. China is leagues ahead of us because they've done much better than us in various other issues, and we know that. All right. So SpaceX high launch rate brings down the cost. ISRO's vehicles are in a pickle as far as cost advantage goes. It has two challenges: achieving a low cost for its vehicle despite being more complicated than the Falcon, and then second, drumming up enough business to support a high launch rate to bring down the cost and make it easier to get more business. So it may be possible that ISRO has to be happy with a small slice of the pie. The big slices may end up with the private enterprise in US that has been unleashed. Okay, so where is the fun for a university in all this? You hear about this, you read, you know, you are told in television, I feel good about it, and then that's about it, right? I wasn't going to settle down to that. I was involved in designing experiments for the space shuttle and the space station, and when the funding kind of started tanking, I said, hey, it's about fairly easy in the US to use propellants and rocket motors and things like that. It's not easy in our place here. There's safety issue, there's explosive hazards, and then there's always getting into the wrong hands and things like that. Much of it later. So where did we start? Well, cosmic coincidence is a good word. It comes from our back books. Private access to space, internet and connectivity, so you don't need to be in Southern California, Silicon Valley, or Boston I-28. You don't need those big schools. NASA came along. NASA has the university student launch program. NASA Marshall, where all of the big rockets were designed to take people to the moon, is 80 miles from Vanderbilt University. So I thought, there's game on. Let's give this a game, and let's make this happen. We had a drastic change in the quality of engineering students. We made need-blind admissions, and in 2005, the quality of our students improved both at undergraduate level and graduate level. They're about the best in the world at this point. Students write these great essays to get into undergraduate schools, and for example, graduate schools too. They want to make a difference. They like to build something from scratch. They want to take charge. They want to discuss big issues. They want to do leadership, and graduate students want to improve their careers and so on. So what is this magic composition? So I looked at the NASA Goddard Space Flight Center. They have 60% close to bachelor's degrees, some 11% doctorates, and 35% master's degrees. So I set up a team, and currently it has the same flavor. Master's students work for master's theses. PhD students put this into as a chapter in their work. Undergraduate students design the whole thing and execute the project as part of their senior design program. The focus was on propulsion and energy conversion. Safety, risk, and hazard analysis becomes very much an important aspect of this. So this was well taken. So this thing came along. It had to be for everything that we do, and I'll point out what it is. And then we can also say, well, All universities don't have to be number one. Is MIT number one? I don't think so. I've walked the corridors of MIT. I'm not just enamored. Things have changed. It changes glacially in the rankings, but you walk there, I don't know, what is this number one? What's the difference between one and you can't find out that difference, okay? We cannot be obsessed about it. We have to be best at something. So, well, at the most they'll say, Stanford, Stanford is good for AI and stuff like that. MIT is good for robotics and things like that. Well, Vanderbilt, yes, Vanderbilt is great at student launch, at launch. They have a great launch program. That's what we wanted to do. By the end of this presentation, maybe you will buy into it. So what's the current trend in engineering? Students are interested in space, but with a new twist. We have to accommodate their desire to design the whole thing and not just be a small cog in a big wheel. The program at Vanderbilt has been designed to generate the new generation of space engineers by giving them the opportunity to design the whole thing, which is the vehicle and an innovative payload. So innovative payload, that's the word that's very important, using modern developments in engineering. The flight vehicle is built around an innovative payload. Remove the payload out, it's just a shell. Nevertheless, a shell that can handle 15G and heavy forces and stuff like that. So what you put in it is what is important. And that is where you need to get the niche. You need to get that separation from others. We have all these new tools in the classroom. Computer-aided design, stress analysis, computational fluid dynamics, carbon fiber materials, structural health monitoring, laser machining, additive manufacturing, mechatronics, IT, software integrated systems. Well, you will get into an engineering school and they put you, your metallurgy, your civil. I think all of this is junk. You learn all these skill sets and solve a real systems engineering problem. That, in my opinion, is the way engineering should be to the future. You come thinking that's what you do, you leave without doing any of this, and you will then start getting harassed about what did I do. You go get a business degree, do this, do that junk, and never be an engineer. Well, you think about it. So what are the big civilizational challenges? There is sustainability and there is global impact. Students want to have global impact. They're always interested in sustainable approaches. It's no longer the approaches of the past. You just throw things away or destroy things and things like that. So systems engineering tries to engineer systems by putting all these things together. So systems engineering is now a very important aspect of aerospace engineering. It has taken precedence over dynamics and fundamental topics like dynamics, structures, and fluid sciences. Students don't get to implement it till they get a job. Students must be able to take into consideration sustainable engineering and global engineering principles. Systems level thinking skills come naturally to students who are cut out for leadership. Let's say that's the kind of emphasis we should be placing. So this is systems engineering. Oh, you build your best bridge, the truss structure, design, and all that. You also have to be thinking about the main purpose, which is to cross this river, and therefore the loads and having that track. So systems engineering is about common sense at every step of the way, apart from the details that go into it. So then it comes up, so what are these projects that I'm itching to tell you? Well, there needs to be criteria. You can't do the same thing that others do, then it's worthless. So projects have to be something that students understand. This is very important. Students need to own that project, They need to understand what it's all about. It needs to tickle their imagination. And it has to be unique with sound engineering principles. It always has to keep sustainability in mind. And for the advisor, it's very important how you take a complex project, break it down, keep it simple, but keep moving the goalpost so that you can achieve more and more and more. So, global engineering principles, I think ISRO has done a marvelous job sending the orbiter mission to Mars at a very low cost, and they talk a lot about it. But obviously people will want to see more of that. We'll see what comes out next. So I'm coming back to the launch program that has been built at Vanderbilt University. It's a very tricky thing. If it takes 8 minutes to go to low Earth orbit, we get less than 16 seconds to play with. Failure is not an option. High speed and high acceleration and deceleration. We are talking about 15 G on the airframe. We are talking about Mach 0.6. We're talking about reaching heights of 5,500 feet. So let's look at a systems engineering problem that will come up. There are at least 15 subsystems like this. So you put a rocket up to a certain height. You need to bring it back so that you can fly it again. If you don't bring it back, then it'll go 6 foot under. You put some sand on it, it's done. So all your efforts will go in vain, and it can happen in a jiffy, because from 5,000 feet to 0 feet, even using the simple Newton's laws of motion, you get only 8 or 9 seconds to play with. So what do? You have to deploy a small parachute, and then you start bringing it down at high speeds, and then you deploy another parachute, and then you recover it. You build a logic. You say, okay, my vehicle goes up. When it reaches a certain height, I will keep a pressure sensor. I will convert the pressure sensor data into a logic. The logic then, across a MOSFET, puts out a high current to blow a charge. When you blow the charge, you break the rocket into two, not physically, but along joints that you have designed to break, and then you deploy a parachute. That will start slowing down the descent, so you have better access to controllability. Well, if that thing fails, what do? Then you deploy another charge with a slightly stronger charge, so this time around you can break it. Well, if that does not deploy, what do? Good, it's coming down pretty fast. Well, I will deploy another parachute around 900 feet so that I can take another shot at it. This is going to be coming down faster, so I better deploy my strings. I better design my strings and the parachute to handle higher G loads, because everything is going to be ripping faster. If that doesn't deploy, what do? Gosh, you are a bad engineer and get lost. Don't do these kind of projects. So what it is build sufficient redundancy so that failure is not an option. This is one system, and you have 16 other systems to design on a new project each year in an 8-month time frame, competing against some 50 universities, and for the last 4 years we have won every time. In the last 8 years we have won the Payload Design Award. I'm not done it, I still have half an hour, so hold on to that applause, okay? So let's start here. Okay, go back.
20 college and university teams competed today in the NASA student launch out at the Salt Flats. The team sent rockets thousands of feet into the air, trying to win big prizes and bragging rights. KSL's photographer Mike DiBernardo was there to capture the action.
This is a really neat place. We're used to launching from a sod farm off of just a grassy field. We're with Vanderbilt University from Nashville, Tennessee. Is that switch on? We're setting our rocket up right now, getting ready to fly. My name's Brandon Dimmick. I'm the president of the Vanderbilt Aerospace Club. Okay, come forward. Bring it through here. It's always neat to see the other teams and what they've been doing throughout the whole year. No clue where that is. Yeah, I got it.
Your hard work for this moment.
UNC Charlotte. It's competition, but it's friendly competition. A little nervous right now, but and assuming that everything works real well. We knew that. It's extremely frustrating. It's very disappointing. Sometimes things are outside of your control and there's nothing you can do.
Everything has to be assembled correctly and checked off the checklist. Man, all year's work for this. I'm a little nervous too. Complete success, parachutes deployed, safe recovery. We're just thrilled right now.
I don't know if you've seen that before out there, but it really is fun.
Yeah, it looks pretty cool.
They go way up and you can't see them.
Really?
They go that high. It's really cool. Congratulations.
All right, so what were the projects that were driving these different missions? Well, it has to have, as I said, big civilizational themes. That's what catches the attention. So we looked at a few different scenarios: direct waste energy conversion in flight, converting heat to electricity using thermoelectric generators. So it's a passive, non-active engine that snuffs off heat radially from the exhaust of an engine and tries to run it through a solid-state thermoelectric generator to generate electricity. The caveat there is one wall be hot and another wall be cold. To keep the other wall cool, you need to be having convective heat removal. So you put fins on it, and then you fly the rocket. As the rocket picks up speed, you cool the other wall, and then you start generating electricity. Well, great. All of this happens in 8 seconds. So you engineer your data acquisition system to generate the data, you generate the plots. The big pretext is that in airplane flight, potentially, you can have auxiliary power generation by using some of that waste heat to generate electricity. Like the MH370 for the Malaysian Airlines that just disappeared. Some stories are that all power systems failed. Maybe there must be a third or a fourth level degeneracy put into it where you can generate electricity and things like that. So that caught the imagination. I'll just show you the engine. Another thing that people talk about is, well, when all the petroleum-based fuels run out, what are we going to do with our aerospace engines? Well, people talk about biofuels. Then I said, hey, how about we design an engine that flies as an auxiliary payload on the rocket, but uses biofuels. So we built this engine, and then we ran it on biofuels. But remember, the biggest challenge is to get all these done in 8 seconds. So from start to finish, from atomization, from fuel injection to atomization to combustion to ignition to combustion to thrust generation, all in that period. It's a very challenging thing. And when students do this, they know they can understand anything more complicated. Last year, we designed a hydrogen peroxide thruster, 10 Newton thruster as an auxiliary thruster on the rocket flight, what we call a green monopropellant thruster. It's not an easy thing. You use catalysis, iridium catalysis, to generate the thrust. It's a very, very reactive fuel. Handling it, you have to go through a lot of materials reviews and things like that. Even a very, very low concentration of an alien material can start off reactions, build pressure, blow up the container, and all sorts of things. So that's a systems engineering problem. We worked on a Mars sample return mission. We've worked on reusable rockets. The most important thing is we keep our budget less than $20,000 a year. This is a very important thing. We're not like a millionaire's club or anything like that. So this is what I was telling about. This is the engine that was designed. It was put on the back of the rocket. So the solid propellant rocket motor exhaust was snuffed off radially across solid-state semiconductor-based bismuth telluride devices. And in real time, data was generated to look at the effect of the convective speed of air, which is the flight speed of the rocket, on generating electric power. In a second version of this, liquid nitrogen was injected on the fins to cool the fins down to conditions that were comparable to flight at 35,000 feet altitude to increase and improve the Seebeck efficiency for energy conversion. Here is the data. So normalized convective heat transfer through the fins as a function of flight speed, direct correlation, showing that flight speed is the player here. Power generated as a function of delta T, which is the standard criteria in Seebeck related energy conversion. You have the standard no augmented cooling thermoelectric generator, and with augmented cooling, it achieves all the 16 watts for which the device is designed for. This is data generated in the 8-second rocket flight. It's extraordinary. It was published and all sorts of things. Then we moved to jet engines. We built a ramjet engine that flies as an auxiliary payload, and then we injected fuel in this engine, ignited it, and generated thrust. But you have to remember one thing. In rocket flight, the thrusting happens for 2 seconds. After 2 seconds, the rocket is in free fall, so it's in standard deceleration, not at -1g, but like -3g, because there is aerodynamic drag also along the axis. So what happens in a liquid container with air on top when it goes into this -3g? It starts sloshing. The position of the air and the liquid gets reversed. So wherever you have the pickup, you have air. So if you have air in the line, it will quench the engine. So first and foremost, you need to design a slosh abatement system. So you need to put together a testing protocol, a design protocol, a flight protocol for a slosh abatement device. And then here is, I'm going to go through the steps. One is the hand-built engine that the students did. You know, the laser can be used for the CAD drawings, and then cutting all these things together, welded. So this is the interior combustion chamber, and this is the finished product. You know, there's a lot of testing. I won't play the video there because I want to keep it within the next 10 to 12 minutes. But students do every aspect of it, including the ground-based testing. So how do you simulate flight conditions? Well, you can't put it in a wind tunnel because the exhaust here is insane. So you put a leaf blower, speed up the air, and then ram it into this engine. So then the engine will raise the pressure, and then you inject the fuel, and then start the combustion. How do you start the combustion when all of this insanity is happening so fast? So in a standard jet engine, there's a pilot flame. That pilot flame is going to be blown out in this kind of a launch. So what you do is take a pellet, a shotgun pellet, powder it, and then put an igniter in it, and then run a high current through it at the right time, and it just blows up. It just goes up. And then it starts the precursor flame. And when you inject the fuel, then the fuel starts igniting, and then it's sustained. So it's a very complicated process. I like those kind of things. All right, so these are the teams that you see as you go along. So fuel system testing and validation, you got to validate the fuel delivery system, the retention system, the storage system, the slosh abatement system, the pressurization system, the control system. So you need to check for leaks, you need to check for safety, you need to check for strength, you need to check for the biggest of these things, which is the abatement of the slosh. You have to check during launch, subscale launches. You need to check during using hydrostatic testing principles. You need to do it in a drop test stand. All of these things are new projects each year, and it's done by a team, and it's executed entirely. Failure is not an option, and you just have to finish this project. So these are some CAD renderings of the fuel tank, delivery system. This is the air tank. This is the solenoid, the electronics. The G switch, it gets it going. They push air into it, pushes the fuel out through an atomizer and things like that. Here's a CAD rendering of the different parts and components that go into a typical section of the rocket. Here's a fuel management flight. Basically what we are looking at, mesh screens trying to hold back the liquid as it goes through rapid deceleration. So you have these slosh abatement discs with screens. In this flight, a GoPro camera is looking at it. We left a small gap between the pickup and this disc. You will notice how fatal it is in the results. This is the level of the fluid, and what you're seeing here is actually what is out here. It's reflected there. So let's play this video in a rocket flight. So the liquid is trying to go up, the air is trying to come down at that rapid deceleration, and the slosh abatement device is trying to hold it back only for that long, and through that small hole, air starts coming in. So maybe, as good engineers, we should look at it again. Okay, maybe. Okay, watch here, watch here. So that's not a good design, because at some point it's going to blow the engine out, blow the flame out, and you won't be able to sustain combustion. So the requirement is you design a slosh abatement device. The final design we came up with is some complicated abater with a bobbin kind of placement, so the air goes completely crazy trying to come through all this. And so the extraction is almost like a horizontal plane just coming down. It goes through 14G and then -3J. It doesn't see any of it, and the project is a success. That's the final product. These are the engines that were run on flight. This is a video that takes us through the entire launch. I will just show you the launch, and maybe you can buy into
Vanderbilt Aerospace Club has liquid fuel management and a ramjet performance, as well as the landing hazard detection. This is going to fly on an L1395. And it's going to come out with a main at 700. This is on pad 44, and we're going to launch this rocket on pad 44 in 5, 4, 3, 2, 1, start. Beautiful blue flame. There it goes. There's the ramjet. Still going. Straight up above. Everybody point at it. It's straight above us. There's an event.
That looked like we had an event on the way up. Yeah.
And there's something underneath the drogue.
I think it came out before Apogee. Yeah, that was the ramjet. What looked like a second stage. Yeah, that was that. What were you guys using for Apogee effect?
This is worth watching, so let's just keep
Okay,
it
it's
through.
straight above us. Point at it, because it's still exactly
That's
straight
the
above
drogue
us.
that's been
It's
deployed.
moving a little bit east of the flight line, but it's still really close.
Yeah. I don't think the whole rocket's there.
There's two items, both attached by a harness with a parachute in the center. And you can see it like doing the dance in the light up there. A greenish color, white color chute.
Yeah, there it is coming down really straight.
Again, it's looking for a main at 700 feet. It's still got a little bit of time here, running through about 1800. It's going to be real close. We'll get to see it all come out. There's about 1200. We're looking at a 700-foot main here. It should be a dot now. There it goes. Man, listen to the whoots and hoots from Vanderbilt. Awesome. Beautiful shoot. That beautiful sky right across the salt. Awesome. Absolutely fabulous.
So listen to an interview that my students are doing with the TV and imagine yourselves being part of that kind of a process. And my presentation here is to stimulate you not to be launch engineers, but to be those kind of engineers who are going to be very passionate about how to present their project, how to own their project, how to design their project.
Liquid
Let's
fuel
go.
management system. So we had a small aluminum fuel tank on board with some liquid fuel inside, and inside of that fuel tank we had a series of baffles to abate the slosh. After main engine cutoff, the fuel wants to slosh around, so we want to prevent that so we can deliver fuel to a ramjet engine. So the ramjet is the second payload on our rocket. It's 4 inches in diameter and it has a gas canister design similar to what you see on real jet engines, but minus all the moving blades and whatnot. So the fuel delivery system is pressurized at 450 psi, and so we have an air supply tank on board and a solenoid that's controlled a certain time after launch. We open the solenoid, and just after main engine cutoff, we ignite the ramjet and try to sustain combustion for 8 seconds. So we have a series of instruments on board that we can collect thrust data and temperature data. So we'll use that data to verify that we indeed did sustain combustion and to validate our slosh abatement system. So.
Well, that is really impressive. So the second plume of smoke that we saw was the ignition of your ramjet, is that right?
Yeah, that's correct. So just after main engine cutoff, we ignite the ramjet at 4 seconds after launch, and then at 5 seconds after launch, we ignite a backup igniter, and that's when we expected ignition to begin. And then we go for about 8 seconds after that, and then we close the solenoid and then reach apogee.
Oh, that's fantastic. So were you getting real-time telemetry data that was telling you that it was functioning? What kind of information were you getting in real time?
So there's a rocket data acquisition system on board that collects all the data. So we'll analyze that post-launch, and we'll look and see what exact data we got.
So you were able to get some additional thrust out of that, almost like a second stage?
The thrust is minimal. One of the requirements is that the thrust does not exceed the drag.
Okay.
So it's just an experiment to look at combustion efficiency, and validate the fuel system.
But you also were trying to hit a target altitude, right? So you had to calculate in that effect to get to your altitude, right?
That's exactly right. So in addition to the wind effects, we did have to account for that because it is negating the drag a little bit. So.
Well, how awesome is that, folks? A ramjet on top of a rocket. Congratulations to Vanderbilt. It's awesome.
Thank you. Thanks a lot.
So you notice pretty much whatever I described, these kids are able to describe. They know this project inside out, front to back to front. That's the kind of passionate ability to express is very necessary in today's project. I'm going to describe one more project. Do I have 10 more minutes? Do I have it? Okay, good. Okay. So NASA said your advisor is a propulsion guy, he's giving you heads on, and you guys keep winning this. We are going to give you a robotics challenge. And so level the playing field, bring MIT, Stanford, and Cornell, and all those people. I said, okay, bring them on, let's see what happens. So the challenge requirement was a simulated scenario on Mars. NASA by 2020 is expecting to send an unmanned mission to Mars to collect a Mars sample and bring it back to Earth. The idea here is in a workspace, pick up that sample, put it in a flight rocket, launch the rocket, and bring it back to Earth, bring the sample back to Earth. So in a simulated scenario, what they're asking for is to pick up this dog bone sample and put it into, so let me show you a CAD rendering of how we went about doing the project. So basically we have this arm, it has a camera on it, and then it's a QR code detector on it. The QR code is on this, it basically detects the location, measures it, and then takes the sample, and it's able to put it into the space, and then a magnetic interlock switch will close the rocket, and then the rocket is righted, and then it goes and fly, and then deploys the sample, bring it back. We did all of that. The most interesting aspect of it is how it does in real time and how the machinery looks. So let's listen to this.
Each year, Vanderbilt University participates in the NASA Student Launch Competition. This year's competition required the construction of a series of autonomous ground support equipment that would allow us to retrieve a payload and place it into a rocket bay. Here you can see the Autonomous Ground Support Equipment, or AGSE. The AGSE begins by resetting itself to an initial position. This position is logged by the onboard controller. After reaching its initial position, the AGSE signals the rocket payload bay to open using a custom-built magnet-locked wire. The AGSE then begins to seek out the payload. It uses a series of short sweeps, analyzing the perceived images from a webcam. These images are filtered, thresholding out noise and detecting shapes and colors. When a contiguous set of colors and shapes appears, similar to the payload's description, the AGSE analyzes the image and centers itself over the top of what it perceives as the payload. This image and position are stored on the AGSE for later use. A signal is sent to the user interface panel that the payload has been found. With the payload found, the AGSE then seeks out the open payload bay.
Full sunlight, no clouds, no way.
Fiducial markers are present on the inside of the carbon fiber plate that will house the payload. These markers provide a line along which the AGSE will eventually place the payload. The AGSE camera seeks out these fiducial markers.
That's the camera there. Seeing straight down.
Upon recognizing the patterns, similar to a QR code, the AGSE is able to detect the payload. A signal is again sent to the user interface panel to indicate that the payload bay has been found. After finding both of these locations, the AGSE returns to the payload. It orients its custom gripper along the axis of the payload, slowly descending. The gripper claws are able to close around the payload and provide enough friction to maintain it. The AGSE rises and slowly rotates back around to position itself above the payload bay.
time. So real time.
Once it is above the position recorded as the payload bay, it again descends, and, positioned closely enough so as to avoid any damage upon landing, it releases the payload into the bay. A signal is sent to the payload bay to close, and the payload is secured inside the rocket body.
So basically the rocket section closes, writes itself, launched, all that good stuff. So what had happened, so all other schools which are supposed to be great schools of robotics, systems engineering is not about being a great school in robotics. It's about getting the job done, knowing all the aspects, dotting the I's, crossing the T's, and getting to the finish line within a short period of time. So this is what it is. You cannot get nerded up about certain areas and lose the big thing. So it's about getting it done. All right, we'll skip some things. So this year we worked on a hydrogen peroxide thruster. It's a supersonic jet, a very complicated catalytic reaction. The reaction is simple, but handling is very complicated. That's 2 seconds of a 10 Newton thruster that was deployed on the rocket for attitude correction. All right, so that's some of the CAD of that. This shows the actuation, safety issues about, so we got different guys working on different subsystems and all coming to the meeting to make it happen. Structural system, factor of safety at the various locations. CAD, looking at an asymmetric tail cone and looking at its effect on aerodynamic drag. So the project that's coming along this year, it's so complicated that I decided I'll take a break and wander around preaching something else that I've come up with, is take this rocket as it reaches apogee and is in a horizontal flight, basically try to right the rocket. The rocket will generally go nose down and start going down like a projectile. And then you have to save it. But what we want to do is flip the rocket at apogee. It's a moving frame. It could be rotating. So you need to put enough redundancy into your logic. So within the 4-second time frame, you need to rotate the thrusters. These are cold gas thrusters. We are going to just expel supersonically pressurized nitrogen. And basically, we can't expel it in any direction, then it'll be a mess. It has to detect the ground direction, and then, so to detect that, and then use the IMU sensor to do that, and then to rotate the front section of the rocket to the right orientation of these thrusters, pick the thruster that reaches that fastest, and then fire the thruster, and use these principles of mechanics and moment of inertia and things like that. Write it just optimally. And so this is what I'm talking about. Kind of prepare it for landing. I don't want to land it, but just kind of prove that you have a complete understanding of the project to do it. All of this autonomy at 5,000 feet, okay? It's very complicated. So you have people running master's thesis, some working on PhD, and a lot working on their senior design project. Rain or shine, students have done this. In the initial phases, failure was always there. What do we get out of this? A passion to do engineering, systems level thinking, and communication. So who are we? Oh, we like this blind people story, right? Different blind people think what we are, all that stuff. And then they realize that we are actually a mini NASA or a mini SpaceX. And then they realize our budget is only $20,000 a year. So this is what you mean by disruptive engineering. You got to shake the world. What are our accolades? We are the most recognized team at Vanderbilt University's history of 125 years. We are probably the most recognized academic college team in the history of academic competitions. We have won 4 NASA Orbital ATK national titles. We have defeated some 200 odd universities. We have done 6 payload design awards, 3 website design awards, 2 project review awards, 2 educational engagement awards. We have 15 awards from AIAA. We have graduated 52 systems engineers, all in aerospace engineering. 8 are at SpaceX. What else are we going to get with projects like this? Everything else that we talk about at IIT and elsewhere. So I said, what are you going to be doing? Well, you're already doing it, and I'm proud of it. You're already. So I put this up here. You haven't launched it. I said, swoosh, it's going to work. Okay? All right, great. How about take a hospital and break it down from a systems engineering perspective and look at how difficult it is to deliver health care, and how shall we not, why not kick that can for survival forward? A lot of survival is based on how well it's systems engineered. You can do a great operation. You may die of infection. You can do this. The doctor may die of infection because of the patient. There's lots going on there. It's just mind-boggling, and it's all engineering. You can't just sit and say, oh no, maybe this is what the big man intended. No, the small man here never even thought about this thing. It's like that water tank next to a railway track. How about this? I don't want you guys to talk about some app that can hire an auto rickshaw, you know, that kind of stuff, some Zoom app or something. How about a self-driving auto rickshaw? Try to do it. It'll take several years. Try to prove it. You got this land here, you know, you're not going to kill people. You can always try it out. Nowhere else can you try. This is what IIT is for, that space you have. Somebody has, in all this madness, somebody has given this space to do something. Is that right? Just get out of that gate. You can't do a thing. You were going to talk about a self-driving auto rickshaw? No, that's not going to work there. But based on that, are you going to say, why should we design a self-driving auto rickshaw? Well, you got to design that, and then only you know why other things can be put into place. Without that, you can't put anything else into place. And that's where we have failed. And that's why I say the way forward is systems engineering. It's not your other fields. Sorry, that's only at higher levels if you want to do research and play with your math. But you know, there are a lot of numerical techniques that can do away with all your math that you're so proud about. The only real engineering is when you make it work. Don't keep talking about these apps. You know, if you did it and the next day another guy can do it, it's not worth it. If you did it and you were the only one and you were the first guy to do it, look at them. They're not dumb. They're not just got away with it. They're really, really smart guys who are trying to reinvest in something that will leave a legacy. Does that make sense? So I'm going to stop this talk at this point and say this is the way forward. Thank you.
Thank you, sir, for an extremely amazing talk. It was really illuminating and delightful for us.
Thank you.
The podium is now open for questions.
I am perfectly okay if you don't have any questions, because there's a lot to digest here, because I think listening to it is basically already throwing up a lot of issues. But at the same time, to make this interaction interesting, we will at least take a few questions. How about 3? Who enjoyed this talk? All right, so there's a lot of you, so you should ask some questions. So I'm only asking for 3 of you, so okay. So you knew putting a hand up would be dangerous. Yeah, go ahead. Yeah. Yeah.
Country India is the main agriculture country. So is it possible that to apply the system engineering for the agriculture purpose and?
Yeah, why not? Why not? What is this agriculture you're talking about? Are you saying that the farmer is happy enough to take that kite and go beat that trash out? Or are you saying you're going to build an equipment that could potentially take care of that task?
Physically for equipment.
Okay, so build that equipment. So don't use the excuse of the fact that everybody is just some agricultural fellow, so why should I work on it? Well, why should you be studying all this anyway? So go ahead and build it. The application and will come. May not be for that. Maybe it might be for collecting some trash on Mars or something. For ISRO might make use of it. All right? The intended application is just an excuse to do something. Okay? The idea here is to get that skill. If you don't have that skill, you can't do anything. You'll only read about it on the web and feel good and watch some videos. That's bullshit. Yeah.
So many of the projects involve some serious safety risks. Like,
repeat that.
Like if something like in aerospace engineering, let's take simple case of RC aircraft itself. It can fail or break into some place. Like, how do you deal with this stuff?
Okay. Safety. So you see, the first thing that comes up is this kind of RC aircrafts and things like that. RC aircrafts are not what I call as systems engineered products. They are test beds, basically. You are putting it through insane working conditions like high G turnovers and things like that. Plus, I don't know if it's autonomous vehicle or it is semi-autonomous vehicle. There's a hand-eye coordination issue. Though you might have played with joysticks and Nintendo and things like that to find it there and internalize the fact how to control it. In fact, when I started this, and the first project I worked on was to deploy a UAV from a rocket at 5,000 feet, take full control over it and fly it. So what happens is you deploy the UAV at 5,000 feet, a robust wing, so it then spreads its wings out, it becomes a flyer, and then it basically it's not under control, so it's kind of gliding, and then you take control at 2,500 feet, pull some sorties on it, and then land it. We actually did that project. It was so interesting that NASA was disinterested in it because that's not what they were interested. They were interested in a combination of science leading to engineering, leading to a big problem solving, not a technical kind of activity. The UAV business doesn't do any science. It's just basically looking at a technical thing. When you shrink the size, despite all the analysis that you do, the biggest things is the G levels go up and things like that. At that point, failure is going to stare at you. But ask the other question, were you designing this for fun? Were you designing this for a task? If you were designing this for the task, back up the parameters, find the operational window where it will be successful, and systems engineer it. So when you're breaking these things up, go back, identify a working window at which it will never fail, and then suggest that if you want to do this, to pick up some Zika samples or whatever you want to say, then work in this window. Engineering is all about identifying a window and sticking to it. All right? Failure at the testing phase is okay, but failure after the prototype is bad. It's really bad. All right? Does that answer your question?
Sir, you showed that picture of the abnormally large guy and very thin guy.
Yeah, I like that picture.
So,
yeah.
And when you speak of Jeff Bezos and Elon Musk, I see that the extraordinarily big guy is the big people like Jeff Bezos or Elon Musk, and it is us who is standing next to it. And
fantastic, fantastic. I like that. But me and you are not Jeff Bezos. That's an outlier. How many Jeff Bezos are there? Only one, right? What about us earthly creatures? Can we use that analogy? Can we all try to be Jeff Bezos? That's the centrality of what I'm trying to say. So you and I can't be Elon Musk. If you cannot try to want to be Elon Musk and then kill millions of people along the way trying to be that one person. I think if the entire energies are spent on those or people, we have never created such people, okay? Sorry, IITs or not, it doesn't matter. We haven't created such people. Let's concentrate on the paradigm that works for us, okay? You found an exception, I like it, but I'm not going to say that is going to drive us.
I was about to ask, there are people who have actually followed their passion, but I think a lot of...
they are not people who followed their... Yeah, go ahead, I can correct it later, yeah.
So, because I was...
okay, go on. What was your question?
Like, how is it that we can align our careers or anything with our passion or something? It's something
very good. You're asking for that puzzle, all right? So you have to hide your core passion in the midst of the world, okay? So maybe I'll give you my example. It may be half true, but maybe it's good enough for today's conversation, okay? So I really wanted to be an aerospace engineer. I came to IIT, and they have these sorting categories. I had a good rank, better rank, so I veered towards mechanical engineering. It's easy to get a job. Mechanical engineering is sort of flexible, they say. My dad was an aeronautical engineer. He was quite disappointed about what I did. And then, and he wasn't officially, he didn't go to any aeronautical school. He basically became an aeronautical engineer working in Hindustan Aeronautics Limited. He knew everything inside out. So coming back to my statement, so I wanted to be an aerospace engineer, so I kind of hid that. So I hid that passion. I waited till the right moment, and that was when I went to graduate school. And then I asked myself, all the developments were in CAD and CFD, you know, all that kind of stuff. I said, no, I want to be a hands-on guy. So I changed advisors and wanted to be a hands-on guy. And then I realized we were working on a very fundamental problem, so I changed projects, okay? So I wanted to be a guy who engineered everything, all right? Then came the job time. I didn't like this tenure track business about some kind of sardine can approach where you take on something and then you get on and then you get on this bus and then the gravy line, this, that, you know. I said, no, I want to design. So I said, I'm interested in space as it's happening. So I picked, so you have to be, well, anyway, so I picked to be a scientist for the space shuttle programs and then the space station. And then when that started turning down, I said, I'm going to pursue this differently. Well, I'm not a Jeff Bezos. I'm not Elon Musk, okay? Get that clear. But I'm telling you, you are neither that. So try to do something, keep your core process, okay? So don't allow that core to change or compromise. But the rest of it, you have to play the world, because you have to still live, right? You have to still. But just going after, I'm going to be this, I'm going to make money here, that's all going to turn to, go find out about, like Alcoholics Anonymous, there are many fellows who went to do things and they've all ended up being, you know, depressed and destroyed and things like that, because they compromised on their core principles of what they wanted to do. Did I tell you something? Did I tell you something? I think just keep that core going, it'll come through. Okay? Scenarios, when they open up, push it through, because you will have that vision, because that's there. But don't waste it all. Just keep that and then invest it at the right time. Okay? Are we done? I can take some more questions. I got energized now. It's good. Okay.
Thank you, sir. It was really a pleasure listening to your talk today. I would now like to invite the Dean I&AR, Professor Nagarajan, sir, to present the token of gratitude to the speaker. We would like to thank all the members of the audience who came for the event today. Please note that we have 2 more sessions organized for the 17th and 18th of August. Keep an eye out in the mail. Thank you.